Hello and welcome. My name is Don McPherson. I am Technical Director with HydroComp, and I welcome you today to our webinar on Rapid Design Space Optimization with NavCad Premium. On your screen to the right, left-hand side, you should see a chat bar. Any questions that you would like to send to us, please forward them through the chat bar, and we'll try to answer questions either during the course of the webinar or at the end. If the question requires an audio connection, we can make that happen as well. For right now, I would like to get just a quick audio feedback from the attendees that sound levels are acceptable and you can hear me okay. If you can just pop back a quick chat if you're having any difficulty, that would be very appreciated. Okay, looks like everything's good, so we will proceed. Rapid design space optimization is a term that we have begun to use here to describe a search within the design space for optimum outcomes. And the rapid design space optimization is to indicate the general cost and speed associated with it. We view this as a preliminary step and one that allows naval architects to focus CFD resources on high-value computations. It's no surprise to anyone that CFD is an amazing tool, but it is one that has a learning curve. It requires some knowledge and certain computational resources. And the objective of rapid design space optimization, or RDSO, is to avoid irrelevant time and expense when you are conducting your CFD studies. It's a way to make CFD more efficient and effective, but it also allows you to confirm the big design decisions early. There are some studies that have indicated that 50% of a project's cost are established during the first 5% of its design setting. And if we look at the design spiral graphic to the right-hand side, that's something that all naval architects are familiar with. So what we're proposing is using RDSO for those initial outer design spiral studies and as a preparatory step for leading to more detailed analysis with CFD. Now, as we step back and consider the prediction of resistance and propulsion in general, whether it be by model testing, even full-scale sea trials, CFD analysis, or parametric studies, they're based on single observed points. And each point is a unique combination of speed. In most cases, it's a steady state speed, a mode, a transit mode, or called free run, even engine idling, or a towing mode, and the ship's loading, which is typically described by its draft and trim. Now that creates just a single observed point of analysis. The full story, when we're looking at a design objective, may require multiple speeds, multiple modes, and multiple loadings. This requires many numbers of calculations and sometimes iterative calculations, particularly where the top speed of a vessel during its design phase may be unknown, and the objective is to achieve a maximum speed. So if we don't know what that top speed is, it will take multiple calculations in order to identify and evaluate what that maximum speed will be. So the point of all this is that A prediction of resistance and propulsion for naval architectural design is more than just a single calculation. It can be many, many calculations representing many different individual characteristics and parameters. Now, to put everything into context, let's briefly review resistance prediction options. And for the purposes of this study and presentation today, we're going to focus on resistance. There are three different orders of calculation that I have here and am describing for you. And I'd like to use the image in the lower right-hand side as a way to describe this. What we're really concerned about when we talk about bare hull resistance, for example, is the immersed volume. And we can see that the immersed volume in its highest order can be described by its envelope, its wetted surface, or the distributed immersed surface. That's the description that CFD will use, its full 3D shape. A simpler method, a lower order method, is to use its distributed volume or its sectional area curve. That's the method that we're going to be describing here, which is the fundamental part of this study with NavCad Premium. It's called a prismatic wave drag method, and we'll learn about that in greater detail here in just a moment. Or for those of you who have run NavCad for an extensive period of time, you'll recognize the parametric methods, where parameters such as length over beam ratio, beam over draft ratio, prismatic coefficient, volumetric fineness coefficient are used. But there are also additional coefficients. In this case, the examples are representing the immersed transom as a non-dimensional ratio against the maximum section area, or bulb parameters. And it's the bulb parameters that we'll particularly be interested in today. Now, resistance prediction fidelity, and by fidelity you could use the term accuracy, is different for each of the methods as well. And so let's look at the three different approaches and put them into context with each other. Now, a parametric prediction has an empirical foundation, such as a systematic series, like the Series 60, or a random data method, such as the very well-known Holtrop method. Now, these represent averaged results, or smoothed results, let's say. And you want to affirm that the empirical data of the hull form under study is within the scope of the method. One of the things that's important about a parametric method is that the effect of sinkage and trim is integrated into the outcome. It's distributed, its resistance includes the empirical effect of any sinkage and trim. Now, the distributed immersed volume method is a computational. It's specific to a geometry, but is a lower order specific, the volume. And it's important that it be calibrated. Now, the calibrated part is something that one must accept, that there is calibration and validation against empirical tests to ensure that the computational outcome is valid. So there still is a scope associated with a calibrated method, because you can only extend its scope to those empirical studies which have proven its fidelity. It includes a simple model for the effect of sinkage and trim within the distributed immersed volume method itself. Now, a distributed immersed surface method, CFD, is also computational. It's of a higher order, but specific to a particular geometry. It also is typically calibrated to empirical data. And it requires a calculation or a priori definition of the sinkage and trim. That's an additional variable that must be resolved in the CFD calculation, which is included in the other two. Now, resistance prediction cost should be well known. The computational time of a parametric method, fractional seconds, almost instantaneous on any business computer. Its model is parametric, so it's a very low capital and operating cost expense. The distributed immersed volume method, the PWD method, its computational time is seconds. It has low capital and operating cost. And the distributed immersed surface method, CFD method, its computational time for a single design point is typically in the hours, and it has a higher capital and operating cost. Now, just a brief comment on propulsion prediction. It's necessary for the complete picture. It has comparable issues of method, fidelity, and cost that was described about the resistance prediction. Now, many of the contemporary design considerations or performance objectives are often about fuel consumption and emissions. And in order to get a good overall fuel consumption, we typically have to describe things by operating modes and a duty profile. And we use key performance indicators for overall energy usage. And we'll show a simplified version of a key performance indicator here for our little case study that we'll be describing. Now, the case study that we want to present to you right now is a research vessel that was looking to have a bulbous bow retrofit. We were given a CAD file for the hull and emission duty profile. And our objective was to narrow the scope of the parameters of the bulb before CFD. There were some interesting priorities that were given to us, that it needed to be a producible bulb. And so this graphic here illustrates what the shape was. It was a hemisphere on the nose attached to a cylinder, which then had some simple fairing into the hull. And the matrix for our design space optimization was the diameter of the bulb, the extension forward of the bulb, and the vertical center of area below waterline. For the hull executive, the administrative tool actually running the calculations, we're using Excel. And the creation of the geometry, both parametric and for the distributed volume, were simply created inside Excel using equations and algorithms. Now, we were seeking a qualitative difference. Not only were we interested in whether a bulb in general is going to be better than no bulb, but to find the characteristics of the bulb that gave us the least overall resistance. And we're connecting Excel to NavCad Premium in order to achieve this. Now, the method that we're going to be applying here is our prismatic wave drag method, which is a wave theory calculation based on an integration and calculation of transverse and divergent wave systems. You may be familiar with calculation methods such as Mitchell's integral, or linear code, or slender ship theory, or thin ship theory. They all form a common calculation methodology. This is a novel implementation of that, where we're using the calculated distributions of sectional area, the vertical center below waterline of that sectional area, and the beam or the waterplane distribution. It does not use surface cuts. And it can consider the shape and position of the bulb as a part of the analysis. One of the first things we wanted to do is to do that calibration study. We wanted to validate it quantitatively to see if the prismatic wave drag method would be appropriate for a study of this type, including the hull form and the characteristics of the bulb. This graphic here is a comparison of the prediction of two parametric methods that fit the scope of the hull very closely, the Ortmerson method and the Holtrop method, against the prismatic wave drag. Quantitatively, these provide very good results and good confidence and confirmation that the PWD method would be quite suitable, particularly given that we're really looking for a qualitative outcome, a comparative outcome, but it also has proven to be quantitatively very strong and reliable. This is a description of the geometry that is used for the prismatic wave drag method. So our added bulb series, our study matrix of the three different variables included the extension forward, the cross-sectional area or the diameter of the bulb, and the immersion of the bulb itself. Particularly look at the nose here. The graphic shows our water plane distribution or beam, our sectional area curve distribution, and the immersion, the vertical center of area below the water line. This is the original bare hull without a bulb, and this is one of the examples of the bulb additions. You can see the extension. In some cases, water plane area or the beam distribution will be 0 because the bulb is extending forward of the water plane. You can see the shape of the nose, and you can see how the immersion of the centroid of the area changes to support the geometry of the bulb itself. Now, implementation in Excel allowed us to create a spreadsheet with a geometric matrix, to write a NavCad Premium interface code, and we use scripts to share data and instructions. NavCad Premium has a full scripting engine and a very simple API. We'll see that here in a moment. One of the important characteristics of this process is that we can integrate Excel. Interface is probably a better word. We can interface Excel with NavCad, being run as what's termed a coupled solver. And we'll see in our example, when the calculation is conducted, a little notification window pops up indicating that the interface is proceeding. Once a calculation is completed in this NavCad quiet mode, data and output are returned from NavCad Premium, which is then read and appended to the spreadsheet and evaluated. Once the entire study is done, we can then run NavCad's prediction of sinkage and trim in order to determine that necessary initial state when proceeding on to CFD analysis. An example of the premium scripting is shown below. It's a simple text-based file format and programming interface. And as I mentioned, it can process scripts as a coupled solver in quiet mode. But data is very object-oriented. For example, the beam on the waterline at the transom, or the definition of the transom stern, is shown here as a part of the hull object. So that beam on waterline is 9.14 meters. So you have hull.beam waterline at transom, 9.14 meters. Same thing with the immersion draft at the transom. Not only is data easy to create in a script, but you can also create processes. This example here shows a command to open a file to run the resistance prediction using the settings and data that have already been established and saved in the file, and then to resave that file new. The last lines are to show one of the graphing options as an example of what you can get out of the NavCad scripting. Is we can compare two files, set line styles as markers and splines, set the particular axes that you want to show, and then export this as a particular JPEG file. We extensively used this feature recently in a Series 64 study that we did, where we were comparing analytical predictions against model tests. So we were running the calculations, producing graphics that we could very quickly evaluate and proceed and collect the entire series into a single document. Now, running NavCad Premium as a solver or a calculation engine, as I mentioned, it processes scripts. There are instructions and samples in the help documentation to get you started on both the interface side, process side, but also the scripting side. One thing that we've done with the interface is we use a text-based data exchange. And the reason for doing this is it allows us to run NavCad, which is a Windows program, on dissimilar operating systems. For example, you could have an executive program on Linux, so long as it is on the same network, to run NavCad on a different Windows computer as a coupled solver and then return the data back to the Linux executive. So it would certainly be possible, for example, that the CFD tool itself could be running NavCad as a coupled solver in support of its own calculations. And then the executive polls for completion of the calculation to capture the results. The example that we're going to use here is to use Excel as the administrative executive program, and we're going to shell and interface with NavCad in its quiet mode. As I mentioned earlier, the bulb variants were developed directly in Excel, not in CAD, using simple geometric formula, but in a CAD program that supported macro or programming capabilities. It would be very easy to allow the CAD program to develop the geometric formula and shape data and shell that to NavCad. Now we're going to demonstrate a connection, calculations, and output. And the duty profile objective, we're using a simplistic time-weighted effective power to illustrate what we're trying to achieve here. We're going to proceed with a video of a calculation session. This is a utility that we wrote to run NavCad in server mode. It has a lot more than you need here typically, but it allows us to document all of the different steps to ensure that connection is made. You'll see down in the system tray the little NavCad icon that shows that NavCad server is running. And the process that you're viewing here is code in Excel that is creating the geometric variants, pushing the data via scripts to NavCad, retrieving the outcome, presenting them back here in Excel, and recalculating the weighted effective power. Those effective powers are pushed to a plot, just a simple bar graph, so we can see those. I have taken the video and truncated it for time a little bit, but the entire process of running 27 variants in NavCad took about 3.5 minutes. And it's almost completed here to get the variants. Now you'll see in the middle there are 2 or 3 variants which were not run. They did not meet certain geometric criteria that were predefined. It allows you to take an analysis that requires certain constraints and simply not run them, for example. So we can see from the bar graphs, which are the better of the bulb characteristics and which have a higher weighted effective power, and then we can use that information to develop whatever design decision makes sense, incorporate that with our issues of producibility, stability, maneuvering, etc., and we can then proceed. Implementation in other tools is just as easy as it would be in Excel. It's all a matter of taking the code, connecting NavCad, creating the proper scripts from the data, pushing that information, and bringing that back. Some examples that I've listed of connections that people have made, users of NavCad have made, are with Rhino 3D, the CAD modeler, and its Grasshopper algorithm modeler. That allows you to take the data from Rhino, push it through Grasshopper for the connection to NavCad Premium. MATLAB and Simulink should be very easy to understand. That's really little more than just an extension of what we saw with Excel here. And Cases is a tool by Friendship Frameworks in Germany, and that's a CAD tool that has an integrated optimization capability. And this graphic here was from a technical paper and project that we had run with them last year for a development of an optimized submersible AUV hull form, including integration of resistance, propeller selection, and propulsion. On the NavCad Premium page, there's a link to a technical paper that can give you more details about that particular process. But this flowchart is reflective of any kind of connection that you would make between any executive program and NavCad Premium. And just as a review, NavCad Premium, rapid design space optimization for CFD. Our objectives are to apply CFD resources effectively. You've made an investment in a very powerful and useful tool. Applying NavCad Premium as a preparatory step for that can save you time and cost and improve your confidence in the results by narrowing the scope of the parameters for the CFD study, so you have a better idea of where you're going to find the best outcome. It can predict the top speed before applying CFD. Let NavCad do the iterative calculations of finding the top speed. Also, let NavCad predict your initial sinkage and trim for you. You don't have to incorporate that as early stage iterations in your CFD. Allow NavCad to do that initial heavy work for you. And then you can use resistance and, of course, power prediction for confirmation and quantitative benchmarks. It will give you resistance curves that are based on lower order methods that tend to be more quantitatively sound sometimes. And so if your CFD prediction is showing resistances that are remarkably different from NavCad, you might want to investigate why that is. Is your model appropriate? Are your parameters and settings for CFD appropriate? Have you gridded it properly? Is there something that is missing, or is it just a matter of scope? And NavCad's predictions might help you identify where shortcomings are in your CFD outcome. With that, I'd like to thank you for your 30 minutes of time today. Reach out to me at HydroCompInc.com. My email address is there. I just want to let you know of a couple upcoming webinars for NavCad in the next few months. We have a getting started with interface with Excel. We have a getting started interfacing NavCad Premium with Cases, and we also have a proper bollard pull calculation with NavCad that will be coming up here in the next month or so. With that, I'd like to open it to any questions that you may have. Please just send us a chat, and I will be happy to answer any questions for you. Okay, we have one quick question about the differences between NavCad Standard and NavCad Premium. Those of you who have been users of NavCad for a while will recognize NavCad Standard as the version that you have always run. In 2014, we created a version called the Premium Edition of NavCad, which incorporates a number of power user features that might not be suitable or necessary for all users. These include the scripting, the external interface and coupling that have been described here, the prismatic wave drag method also described here, and a full operating modes analysis. That includes the ability to establish multiple modes of operation for towing, transit, idle, and you can get a variety of different key performance indicators out of it on fuel consumption or energy usage by the propulsion system. The other feature of NavCad Premium is it comes with a single seat floating network license upgrade from the standard node-based version that most of you would be using with NavCad Standard. Do we have any other questions? With that, I'll thank you for your time again this morning. At the conclusion of this, there'll be a brief survey. If you could take just a moment to send us your thoughts on the webinar, things you'd like to see, things that we can do with this. And have a great day, and we look forward to seeing you at our next webinar.